Oh, hi, my name is Tom Hill. I'm the Senior Manager of DSP Solutions at Xilinx. This is high performance DSP with Xilinx all programmable devices. In this presentation, what we're going to do is focus on what are the signal processing design challenges that we think people will be facing in the next few years. And our next generation development platforms are actually going to support a new analog interface standard called JESD 204B. And this includes the use of our high-speed serial transceivers. And by doing that, in one platform, we've now included high-speed analog circuitry, the FPGA for digital DSP. The reference design is built on an embedded, the reference design is built on an embedded system. So you have a software component to it. And with the introduction of the JSD 204B, we now have high-speed serial I/O. At Xilinx, we actually have 4 separate specialists that cater to these 4 different domains. And today's DSP designers really need to be experts in all 4 of these. And this is one of the big design challenges. Is how do you become proficient, or even how do you even get by trying to develop a design in these 4 distinct domains? So this is one of the big design challenges we'll look at today. One of the other ones is when you are developing DSP designs, to really get the most out of system performance, you need to really tune the analog and the digital designs together. And platforms that enable this can be of great value. And finally, these designs are going to require real-world data so that you can test your algorithms using your data rather than relying entirely on the data that would be generated from a modeling environment such as MATLAB or Simulink. So we're going to kind of dig into these today, and we're going to talk a little bit about what Xilinx is doing with our partners to help people address these challenges. Primarily, one of the big ways we're going to solve this is with a new generation of DSP design platforms. And there are some elements to these platforms that we think will enable their ease of use. First, these platforms do include what can be incredibly complex analog components, analog FMC cards using a variety of chips from the vendors. And you really need to be able to easily program these interfaces from an environment that you're used to. So analog interfaces that can be easily programmed is one way you're going to solve it. Then you want to be able to deploy your signal processing algorithms onto the FPGA or programmable SoCs using a design method that can be easy to program as well. And this really brings us to the use of these new high-level design flows, primarily based on either MATLAB and Simulink or C, C++. Now, that being said, you want to be able to really assemble the hardware platform quickly. That will let you get to an early prototype, explore feasibility, even to do initial development. And in order to enable this, it's incredibly useful to have a large ecosystem of interchangeable analog FMC cards. And finally, one of the things that you're going to see that's really new is these solutions are almost becoming too complex for one company to really solve entirely as well. And this is really driving companies like the MathWorks and Analog Devices and Xilinx to work together to co-develop a new generation of platforms that addresses these issues that will enable the ease of use. So partners working together is really what you're going to see moving forward. So in this presentation, what we're going to do is I'll do a quick introduction to the Xilinx all programmable devices for signal processing, for those of you that aren't familiar with them. Then we'll go into some signal processing system design considerations. We'll look at what Xilinx offers for a DSP design environment. And then as an exercise, we'll look at how you would go about designing a typical type algorithm, which would be a digital down conversion block, using a model-based design flow from the MathWorks. And then we'll finish with a quick introduction to what we're looking towards, which is adopting the JSD 204B standard. And then finally, this will become, we'll talk a little bit about the platform that we're showing at the conference today, which is a rapid prototyping platform that we co-developed with Analog Devices. So let's first look at what Xilinx offers for high-performance signal processing. Xilinx, we're currently out with our 7 series FPGAs. This includes 3 different device families. We have the Kintex device, which provides the industry's best price performance. For people that need higher levels of system performance, we have our Vertex class devices, and these include up to 3600 DSP-4881 slices. So these offer a huge capacity, a lot of DSP processing bandwidth. And then for folks that are looking for lower cost or lower power, we have our Artix family, which is really optimized for high volume, power sensitive products. These do share what we call a shared scalable architecture. You could have one design that could become multiple different products with different price points addressing different markets, or you could start off on a design targeting one family, and if it turns out that you need to move to either a lower cost family or a higher performance family, you can do that very easily within our design tools. Almost 2 years ago, actually probably closer to 3 years ago, Xilinx initially announced our architecture for what's now been introduced as our Zinc family of devices. Now here, we are the industry's first programmable logic vendor to come out with a dual Cortex A9 ARM processing system hardened on a device that includes programmable logic. And we call this our Zinc family, and we refer to these as programmable SoCs. We currently have 4 devices that are available now. These have been out for over almost a year and a half. And we do have a number of development platforms as well as partner support for software and libraries available for these as well. But this is the other class of device we have, are the all programmable SoC devices. Now, all these devices, whether it's a Zinc device or one of the 7 series devices, they do share common programmable logic. And with Xilinx, it's really the ability to create custom hardware, which allows us to achieve these high levels of DSP performance. And at the heart of this performance is a hardened macro block on the device. Called a DSP-48E1 slice. This is just a quick overview. You can see from the table below that there are different numbers of these on the different devices. It's our ability to create parallel structures to process these DSP algorithms that gives us a performance. So we have almost 2,000 DSP-48s on a Kintex class device, just under 4,000 on a Vertex class device, and our largest Zinc device has just over 2,000 DSP-48 slices as well. So we do offer a lot of DSP horsepower in these devices. Just a quick overview. These do include a 25 by 18 multiplier. There are 2 DSP-48 slices that are interconnected with 5 high-speed interconnects into what we call a DSP-48 tile. So we can implement wide multiplies and wide multiply accumulates without any loss in Fmax performance as long as we stay within the DSP-48 tile. There's a pre-adder, so for people doing symmetric filtering, half-band filtering, the pre-adder allows us to pre-calculate or do a pre-add on the symmetric coefficients. It lets us do a pre-add on the tap delay line, and it allows us to reduce the hardware by 50%. So it's a key component of it. And then finally, we do have a 48-bit accumulator, and there's a pattern detection on there that can be used to implement rounding modes. This device is dynamically configurable on a clock-by-clock basis, and it can be programmed to perform over 30 different arithmetic functions. So it really is the heart and soul of our DSP solution in Xilinx is a DSP-48E1 slice. And then just to give you an idea, Xilinx, we do offer, in a programmable device, we do offer performance leading devices across all our device families. whether it's the high-volume RTX type devices, the programmable SoC devices that you find with Zinc, or the cost performance device family in Kintex, or the high system performance family in Vertex. Across the board, we do have performance leadership in all the different device families, and this goes for both, like a 16 by 16 gigamat comparison, billion multiply accumulates per cycle, or for folks that are doing floating point, we do have the ability to configure the DSP48 slices into single or double precision floating point blocks, and we do offer floating point performance leadership as well. So there's a lot of horsepower in these devices, and folks that use Xilinx are looking for the performance that we can offer. Now, the 7 series devices do have high-speed serial transceivers. Depending on the device family, there are 4 different transceivers that you'll find in the chips. Some chips offer a combination of these. And we have all the way from 6.6 gigabit per second transceivers with the GTP, all the way up to 28.5 gigabit per second transceivers on our Vertex class devices with the GTX transceiver. In signal processing, our most popular device tends to be the Kintex class devices, and in those you'll find the GTH and the GTX transceivers. But through these transceivers, we can support just a huge amount of serial bandwidth. So down below, we're showing that our Vertex 7 HT device can support up to total 2.8 terabits per second transceiver bandwidth. So this does have 16 28 gig transceivers and 72 of the 13.1 gig transceivers. So this is what we have at the high end, and pretty much everything in between. Then this right here is showing 4 different eye diagrams for the 4 different transceivers. These are the way these transceivers have been designed. Do allow very stable, very clean eye diagram, and this can be demonstrated using Xilinx can show it using our iBird IP within the chipscope or Vivado analyzer environment, or through a third party. These are actually screenshots of actual data going through the 4 different transceivers, and it's meant to highlight how clean the eye diagrams are. So signal processing design considerations. This is really what we're here to talk about today. What we really want to do is to be able to deliver a next generation of platforms that really enables you to, evaluate these considerations and come up with the best designs that you can. And the first thing I'm going to go over with is, signal processing. Typically, what you want to do is you want to like in a wireless, type application, you're going to want to really maximize the bandwidth that you're going to be able to receive across the airwave, the RF signal. In order to do that, you need to have a good signal-to-noise ratio. A higher signal-to-noise ratios really enable more data to get transferred and allows for higher bandwidth systems. So just a quick rundown. A lot of folks may already be familiar with this, but signal-to-noise ratio is really the total Gaussian power. The total signal power divided by the total noise power, and less noise means a higher signal-to-noise ratio. And this does allow you to really support higher bandwidth across the air interface. Now, one of the techniques that's really common to do is to oversample your RF, essentially your ADC. If your Nyquist, if your Nyquist frequency is say 100 megasamples per second, or 50 megasamples per second, then each 1x oversampling is going to give you a 3 dB improvement in the signal-noise ratio. And for every 6 dB of improvement in the signal-noise ratio, it effectively adds another bit to your ADC. So if you're using a 14-bit ADC, but you can oversample by 4 and get a 6 dB gain, then that's like you're using a 15-bit ADC. So it's a technique that people want to use, but using this does complicate the design process. It is going to require the FPGA to clock faster. Higher clock rates tend to dissipate more power, and it tends to make the signal processing hardware more complex by having to handle data at faster rates. But it may be something you want to do, and it may be worth doing, or you may be able to, live with lower signal noise ratio and use less complex hardware, and maybe even get into a cheaper device. So there are a lot of trade-offs, and again, it's really enabling you to make those trade-offs is what we're working towards. Now, if you do oversample, then you are going to, this is going to improve the signal-noise ratio, but in order to do that, it's going to spread out the quantization noise over a larger spectrum. But if you just decimate without filtering, you're essentially going to put the noise right back into the system. So really what this allows us to do is to create a decimation system that lets us downsample back to our baseband frequency, but we want to do this in a way that we can preserve the signal-noise ratio gains that we achieve through the oversampling. So how do we do this? And then basically we do this by implementing a digital filter. Now this digital filter followed by the complex mixing to restore the signal down to the baseband frequency is what we refer to as a digital down converter. So these high-speed analog interfaces almost always have a digital up converter or a digital down converter around them. So what we want to do is we want to spread the quantization noise over a wider spectrum, but then when we go to downsample back to baseband, before we do that, we want to basically filter out the noise so that we can achieve the signal-noise ratio gains without having to put the noise power back into the system. This is exactly what we're going to be talking about here in the lab today. So system design considerations. Higher IF sample rates will result in better to signal noise ratio, so that's a good thing. But when doing that, you're not going to want to develop signal processing hardware that performs the functions at the high sample rate. What you're going to want to do is you're going to want to downsample back to baseband, but you're going to want to combine the downsampling with filtering that will filter out the noise power and maintain the signal so that we get the high signal noise ratio. There is one other design consideration is that the FPGA clocking rate needs to be a multiple of the IF clocking rate. And there are some tricks you can play, but this is one of the big it's one of the big design considerations that we'll go into a little bit is how do you basically play around with different RF sampling rates and different FPGA sampling rates at the same time to see what's going to give you your best system. Now I want to introduce one other technique here which really is going to come into the consideration mix pretty quickly, and this is the simple concept of overclocking. Now, as I had said before, the Xilinx FPGAs have these, up to 3,600 of these DSP48E1 slices. Now, if you're trying to get onto a smaller device or perhaps a smaller part, one of the things that you may want to do is to try to, you're going to want to try to use as few of these as possible. Now, one technique to use these is to do what's called overclocking. And here we're essentially using time division multiplexing to resource share, one DSP48 across, 3 different multiplication calculations. So this is just one example, but if your carrier frequency or processing application doesn't require the full performance of the FPGA, that doesn't mean that performance wasted. You can use that extra performance to implement overclocking to resource share your multipliers and potentially get you into a smaller package or even a smaller device family. This might be all you need to go from, say, a Kintex device down to an Artix device and save power and device cost. So overclocking, it's a very commonly used technique, and it's certainly one that you're going to want to evaluate along with the other considerations. So let's take a look at what Xilinx offers tool-wise to help you do this. So this is an overview of the Xilinx DSP design environment. Xilinx does offer an industry-leading signal processing design flow. We now have flows that are available from both the MATLAB Simulink environment and from C++, and then we also do support a traditional RTL flow. Now, in this environment, Xilinx offers a tool called System Generator, which we'll go into in a moment. But each one of these flows has, either libraries, essentially IP libraries that are usable in the flow. And then in the case of MATLAB Simulink, our partner MathWorks has direct RTL code generation using a product from them called HDO Coder from generic Simulink diagrams. So there are a lot of different design flows that are available. We can generate either fixed or floating point hardware. And kind of what's key to this is we through System Generator, we've been able to integrate these flows to our hardware platforms, and which include the analog FMC daughter cards. So we're able to basically bring RF data, capture it on the boards, and DMA transfer it up into the design environment. Now, Xilinx does offer really a leading portfolio of DSP IP. We do have a comprehensive set of what you might consider, the basic DSP building blocks: filters, FFTs, DDS compilers, basic math, Cortex, things like that. For people that are doing video, we do have an extensive video processing IP portfolio, the Xilinx Video IP Pack. And now, with the recent introduction of our C-based high-level synthesis, we've started to introduce C libraries that can be used in a C flow. And today we have some math functions, some floating point functions. We're starting to introduce some OpenCV functions for video, as well as some linear algebra functions. And then for folks that are doing high-end wireless, we really do have an unmatched LTE library of forward error correction, channel models, FFTs, things like that. So it's an extensive portfolio of IP, and for folks that are looking to use IP like this, you should find a well-populated IP library within Xilinx. Now, System Generator for DSP enables the use of the MathWorks Simulink and MATLAB environments for FPGA design. System Generator is a plugin to Simulink, and it includes a device-optimized DSP library of over 100 different building blocks. And a lot of these building blocks will leverage our pre-developed IP compilers, such as the FIR, the FFT, or the DDS. And you can get literally, code as good as a handcrafted code. In fact, this environment really helps you leverage the collective experience of the Xilinx DSP IP development team, which has been implementing DSP algorithms on Xilinx FPGAs for almost 20 years. This supports automatic VHDL or Verilog code generation, again targeting Xilinx devices. Now, this is integrated into our new Vivado design environment, so you can export designs developed in System Generator into the IP catalog of Vivado. For people that prefer working in the C++ environment, we have a new tool called Vivado HLS. This does support C, C++, and System C, and allows you to write untimed C models that you can then schedule through the high-level synthesis engine. And from that, you can do design exploration, and you can generate RTL designs that provide efficient hardware in Xilinx. Now, working in C, a lot of people like to work in C because of the fast simulation times of C. This can be leveraged to really dramatically shorten development times. And then C becomes your golden source for functional development, and allows you to basically very quickly take that down to programmable logic. We have over 1,000 copies of HLS in use today worldwide, and we do have a lot of customer tape-outs on this today. So it's customer-proven results. We've just, with Vivado IP Integrator, we've just introduced a new way to do design assembly that doesn't require RTL design skills with a new product called Vivado IP Integrator. This is graphical block-based. It does let you interconnect blocks based on an interface view of the design, not on a signal view. So with a single click, you essentially can wire up your DSP data path together, and this will essentially generate top-level RTL code. And this is integrated into the Vivado IP catalog, and you can use Vivado IP Integrator with blocks that are created by either Vivado HLS from C or MATLAB and Simulink from System Generator. So this does support the integration of IP blocks generated from the other high-level design flows. And as I had said earlier, we do have an integrated environment where folks that want to design in C but validate in the MathWorks environment, which is a very common flow, they can export designs from Vivado HLS into System Generator for verification or to be combined with other blocks in the System Generator environment, or they can be exported to the Vivado IP catalog. And similarly, System Generator can export designs to the Vivado IP catalog as well, so that they can be easily added to Zinc or 7 series designs. So all these design environments are integrated. Now, just a little bit about Vivado itself. Vivado is a completely new design environment from Xilinx. It was 4 years in the making. It's a complete rewrite. And from an FPGA implementation standpoint, Xilinx essentially moved from what we had in ICE to really more of an ASIC state-of-the-art, sort of ASIC style place and route environment. So this, we do think that this can dramatically shorten development cycles. It's been designed to really have the capacity that we think we're going to need for the next 10 years. So it is designed with a new database, which will scale to very large devices that we'll be introducing in the next few releases. And then it does help you achieve time enclosure on your designs more predictably, and we think in just a fraction of the time of ICE. So this is kind of an introduction to Vivado Design Suite. And then, at some point in design, you're probably going to need to do some RTL debug. And then Vivado Design Suite does include Vivado Analyzer. And this allows you to insert debug probe points in any view of the design. So you can do it from a hierarchy view, a schematic view, a netlist view, or an RTL view. And then once you do that, the code will automatically be updated to include the logic analyzer, IP blocks, and probe points. So it's all done through properties on the user interface level. And this is Vivado IP Analyzer. So now kind of moving on to the next topic, let's kind of take a look at how you would go about designing. So this is actually going to be a digital down converter using model-based design, and go through the flow here. So I'm just kind of presenting this as a kind of a generic example. Let's say that we've got a high-speed analog card with an ADC in it that's sampling the data at 245.76 megasamples per second. We'd bring this in through either a JSD204B or LVDS interface, either one today. But it's going to come on the chip, and we want to make some decisions on the about the design. What kind of pulse shaping do we need to perform to really achieve our desired signal-to-noise ratio? Is this a wideband or narrowband signal? This is going to affect the kind of digital design converter you're going to want to provide. And one of the interesting questions, and one that we're going to explore today the most, is going to be The digital down converter filters. What are we looking at? If this in this particular design, it's going to need to do an 8x downsample. Do we want to do this all at once? One filter with an 8x downsample? Do we want to use 2 filters, 3 filters, or 4 filters? And how would that look? So we'll kind of explore how, what tools we have today that can help you do that easier. Now, as I had said before, the other area that we really need to look at is IF sampling rate versus programmable logic Fmax. So in this particular example, I've got an ADC that can run up to 245 megasamples per second. But then I've also got a programmable logic device that can run up to 741 megahertz. But if I sample at 245, then I'm going to need to run my FPGA at 245, which means that I may be able to do some overclocking up to 491. But I've just got that one step of overclocking. That being said, maybe I could sample at 122 megasamples per second, and then if I brought it into the device, I could process it at 122, 245, 368, or 491. So, the smaller sampling rate is actually going to give me more overclocking options on the FPGA, and that may be what I want. And it turns out that I may be able to meet my signal-noise ratio specifications, with the lower sample rate. So it's not always a given that you need these higher sample rates. This is really something that you're going to want to play around with in the lab. Now, so one of the ways that we can evaluate what kind of filter configuration we want very quickly is to use a product from the MathWorks called FDA Tool. This stands for Filter Design Analysis Tool. And this lets me do 2 things. It lets me very, very easily design a filter using some general filter parameters along with my specific specifications. And then once it does that, it does almost immediately present a plot of the filter, so I can make sure that I'm still, that my noise floor is looks good and my roll-off frequency looks right. But then it also has this little information button that will tell me a little bit about the hardware on this filter. Now, these aren't directly relating to Xilinx DSP 4881 slices. It's simply telling you how many multiplies NAT it's going to take to implement this filter. But that's enough to see the trend. And if I want to evaluate, do I want to do this in 1 filter, 2 filters, 3 filters, or 4 filters approach, I can do it here in a few minutes as opposed to having to build these up in hardware over probably several days. And this is what the FDA tool will do for you. Once you've determined the kind of filters that you want, it can export a Simulink model of the cascaded filter configuration. And what this lets me do is this lets me build what we call an executable spec. So I've now got a design running in Simulink, and then I can see from the plots that I'm getting the desired response. So here the carrier frequency is 12 megahertz. So this is exactly what I'm looking for. So I can design my my non-implementable DDC in Simulink, and then finally we use this term model-based design to really refer to the fact that I can then design my hardware filter that's going to go on my FPGA in conjunction with my executable spec. So when I design my hardware, I'm going to know immediately if it's functionally similar to the executable spec, or if I just made some horrible mistake. But I don't need to wait till I push this down to hardware and run actual data through it to see if I messed up a bit width or something like that. I can do this all in the Simulink environment. This really helps accelerate the design cycles. Now, in this particular example, it turned out that the 4 filters did provide the most efficient hardware results, and this was what was calculated by the FDA tool. So we went ahead and we built our 4 filter implementation up. We're using a channel filter implemented with a root raised cosine filter, followed by 3 half-band filters that do a decimation of 2. So we do the, I guess in this case, this is the decimation by 16 case. we're doing a decimation by 2 on each one of those to get our decimation by 16 implemented. But what we're showing here in this diagram is I've got an IF sampling rate in this example of 61.44 megahertz. But what I want to do is I want to use the performance of my FPGA, and I've got lots of performance. I want to use some of that performance to try to reduce my hardware. We've actually built this hardware optimization directly into the FIR filter block itself, and that's demonstrated by this one here. So if I don't do anything, this is going to take 27 DSP48s to implement, and we can see that under the second column. Now the third column, if I choose to use time division multiplexing to basically interleave my I and my Q channel for the complex data coming in. So I've still got a 61.44 megahertz sampling rate, but at this point I'm now going to need to double the frequency of my filters so that I can resource share them between the I and the Q channel of the data coming in. And this is a configuration on the filter itself. I'm essentially doing a dual channel filter with a single input, and then it's going to force a resource sharing. It's going to use overclocking to do that. Now the third one is I'm now running at 122 megahertz, but I know that this device can run up to 741 megahertz. I could use some additional overclocking by setting a higher frequency to reduce the DSP count even further. And that's demonstrated down here when it drops to 11 DSP48 slices for the entire down converter chain. So it just gives you an idea how quickly you can go through and really optimize your design for this stuff. Now, so that's kind of just a quick introduction to how you would use the tools to design something like a digital converter. Now, the next thing I want to do is touch on this JST204B. So at the Analog Devices Conference, our partner, Analog Devices, is actually at the show, and they're showing their first JST204B demo on the floor. This is done with an FMC card created by another partner called 4DSP, and this does include JST204B and the ADC channels coming in. Now, Xilinx does offer a JST204B IP core, and this core was used by Analog Devices to build up their design. This core supports the JST204B, the JST204B A and B standards. It supports transmit, receive, and duplex in transmit and receive modes. It supports up to 8 lanes of configuration at 12.5 gigabits per second. Supports for the JST204B subclass 0, 1, and 2, and deterministic latency for subclasses 0, 1. And finally, it supports all of our transceivers except for our high-end Vertex 7 GTZ transceiver. The JST204B spec today doesn't support transceivers with that bandwidth. So this is available today. We've been shipping it for quite some time, and it is available today from Xilinx. Now, this is generated by customers using an easy-to-use wizard. So people can generate their IP core to their specifications using a step-by-step guided wizard flow. And this is going to generate the core, the XCO files, documentation, as well as a Verilog example with the test bench and synthesis scripts. Now, looking at the design a little bit deeper, this is this design. You can see that Analog Devices has actually generated these kind of hardware P cores, the AD9250 core and the JST core. These have been assembled in the Xilinx's Platform Studio design environment into an embedded system. But you can see how the analog data is basically 4 lanes of data is brought into the GTX transceivers, where it goes through the JST204B interface and into the mailboxes of the downstream party. And then on the transmit side, then the data, this particular card, the data is done through an LVDS interface. So JST204B is just used on the receive side. But you can see here that there are these AXI SPI registers. There are hundreds of configuration registers on the FMC card, which can be configured from the Zinc subsystem using a Linux driver file, which dramatically simplifies the setup task for the analog card. Now, finally, Analog Devices got pretty innovative, and they were able to leverage some of the functionality in the Xilinx transceiver IP block itself to develop this iScan diagram, which is part of the reference design, which really shows you the integrity of the eye diagram for the transceiver in an environment that's really free of external noise, external sources. So this is going to do is this is going to let me run my actual data or receive my actual data from the RF, bring it into the FPGA, and then it's going to show me the eye diagram, for my analog interface on my FPGA or SoC. But it's going to do this with real world data as opposed to a pattern generator. And this is available at no cost as part of the reference design. So then the last section here is really just to touch on what's being shown on the floor. We encourage you after this session to wander the exhibit area. We do have various flavors of this platform in a couple different booths. Avnet has one, Xilinx has one, Matrix has one. But what we're showing there is again, it's this reference design. On the floor, it's being shown running on our Zinc ZC702 board. But if you go to the Analog Devices website, they do have versions of this reference design available for all the common Xilinx 7 Series and Zinc boards. So it's basically just kind of showing what's available today and what board supports are available for it. So then, if you do want to see the demo, this particular demo with JSC204B is not being shown at the Xilinx booth. It's being shown at the Analog Devices booth, but I'm sure they'd love to show it to you. This is a whole transmit-receive loop that's going to, use the MathWorks to really help generate a generated signal, through the design to the JSC204B. So in summary, as always, we'd love it if you bought a kit and got started. And to make life easy for you, we do have a Xilinx, it's a Xilinx/Avnet Zinc SDR kit available today that uses the Avnet FMC Comms S1 board. But definitely, buy a kit today and get started. By all means, come by the booth and have a chat with us during the show. We'll be at the booth. We'll have this demo as well as an AMS demo. And then if you do want to learn more, particularly how the partners are working together, each of the partners does have a website that references the other partners' names. You can go to mathworks.com/Zinc, mathworks.com/FPGA, mathworks.com/Xilinx, and you can now go to analogdevices.com/Xilinx. And from Xilinx, we have a xilinx.com/DSP. So, it is an ever-growing list of web resources. But again, it's really the partners, all three partners that are coming together to solve these problems. That's my last slide. So thanks for watching.